we were talking so far about finite dimensional systems, discrete systems. We want to study, of course, in mechanics, we're more interested typically in continuous systems, so-called infinite dimensional systems. Already we have some technical challenges when we do so, because we no longer have this concept of norm equivalence. So when you specify the definition of stability, the definition must include, in principle, to be technically complete, must include the specification of the norm that you're using to assess stability or instability. There are other technical difficulties which we'll come to. So let's, as an example problem, we'll use one example, which is, say, spatial rod theory, nonlinear rod theory, Kirchhoff rod theory that goes back to the middle 19th century, which is the three-dimensional extension of the Euler elastica. And this is the prototypical stability-instability problem in structural mechanics. And I will indicate extrapolations to other kinds of structures that are possible. And then we will talk about the possibility of doing continuum mechanics. And Francesco, immediately I cannot use your computer here. It's frozen.
You know what? I will sit here.
Yeah? Okay. Oh, no, okay, no. Okay, it's okay. You may sit down. So, let me discuss for a few moments before we immerse ourselves again into Lyapunov theory and so on, just the basic model. It's well known, but I discuss it in a way that imitates the program of continuum mechanics these days. Okay? So we have so-called spatial rod. We will model it as a one-dimensional continuum in three-dimensional space. And we can have a force, for example, applied at some parts of the rod. And here's some general configuration in space. And we will parameterize the rod using arc length. And just for simplicity and as a practical matter without much loss of generality, let's take the rod to be inextensible. It's much easier to bend the rod or twist the rod than it is to extend it, change its length. This is not so for shells because of reasons in differential geometry. But for rods, the typical mode of deformation is almost inextensible, provided you do not stretch the rod explicitly and pull on the rod. So at any arc length value s, we can have acting on the cross-section, we'll call it a cross-section, associated with arc length s. We have a force at arc length value s, and a moment, let's say m. Okay, so this is the force exerted by the part of the rod to the right on the part to the left, and the moment likewise. So we look at some arbitrary interval of arc length, s1 to s2, and we're interested in the motion, equations of motion, and so on. So we have an arbitrary interval inside the total length. And let's consider a particular time t, and look at the dynamics of that rod. So rho will be a mass per unit length. R is positioned to a point on this rod. So R of s at a given time is the arc length parameterization of that segment of the rod. And so we have some forces, F2, which is the value of this force function at arc length S2. And F1 we have acting at this point in the rod here. So the total force should then be the rate of change of the linear momentum, which we write this way. Rho, again, is a mass per unit length. And we will treat the arc length, because of inextensibility, we can take the arc length as a convected coordinate, a material coordinate, essentially. If we have stretch of the rod, then we need to modify this. But here we can treat S as a label for a molecule or a particle of the rod. Okay? So it's convected. So if we suppose this inertia is bounded in this interval, and shrink the interval in size, S2 approaches S1, then we find F1 plus F2 is 0. F2 is the value of this force function in the rod at S2. And S2, we assume this is a continuous function, so this becomes minus f at S1. Okay, this is like the idea of when you derive in the Cauchy traction argument, the idea of equal and opposite forces across a surface. It's the analog of that, okay? So then we replace this equation by this, and we can then recognize this as the integral of the derivative of f, and now we can so-called localize this, this statement, or equivalently use the mean value theorem. So the procedure is familiar in continuum mechanics. And we derive the local linear momentum balance. This is like a divergence of the force in one dimension, balanced by the inertia. There's a very nice and reasonably elementary paper on extracting a model like this from three-dimensional elasticity by Dill in the Archive for the History of Exact Sciences. It's quite an educational paper, and I would recommend looking at that. Not too old, 1992. So here, just to establish a simple model, I will proceed from the idea that the rod is really a one-dimensional continuum, and we will account for the cross-section by adding some kinematic and constitutive structure to the one-dimensional continuum. Okay? So in the simplest case, this is the Kirchhoff idealization. The cross-sections of the rod really behave as rigid bodies. The cross-section itself does not distort, and it remains always orthogonal to the center line, the tangent to the curve. Okay? Described by that parameterization R. And let's say T is the unit tangent, and then with T, we call it E1, we form an orthonormal triad on the cross-section, E1, E2, E3. Okay? And so we suppose the cross-section does not strain, but of course different cross-sections have different orientations, and so there's a variation of this triad with respect to arc length along the rod. The so-called Kirchhoff hypothesis. One can actually make this rigorous in a derivation from 3 dimensions under certain conditions, and in the modern literature since 2000, 2005, let's say, you will find the model rigorously derived, at least for statics, by variational convergence methods, but anyway. So let's have a reference configuration, an initial configuration, in which these cross-sectional vectors have some known values, capital E1, E2, E3. And just to make life very simple, we'll suppose this is a uniform triad, so that we have a straight prismatic body in our reference configuration. And then this is a bad slide, obviously, but the initial position is a straight line that's given here, and the direction of the straight line is E1. Okay? With E1 and L is the position of the point with arc length 0. You specify that position, and so on. So if the embedded vectors in the cross-section, to say that the cross-section does not distort means that the embedded vectors deform like a rigid triad at any given arc length value. So that means that these capital E's are mapped to the small e's by some rotation tensor, which can depend on arc length and time. Okay? And so here's a representation for the rotation tensor, which is easy to derive. It's the tensor product of the current values of these cross-sectional vectors, including the tangent, tensor product with the initial values. Okay, very simple. And so we have in mind the idea that the rate of change of this rotation along the rod should somehow be significant for the mechanics. The reason being that the curvatures and twists of the rod are determined by the arc length derivatives of these embedded cross-sectional vectors, and E1, remember, is the tangent to the center line. So this variable r prime, the arc length derivative, will be somehow important, and we can associate it with skew tensor, which is like so. So the skew tensor contains information about the twist of the rod and the bending of the rod. So, okay. And later on, we will see that constitutively, this skew tensor is important for us. We can simplify matters by using the axial vector small w, which is equivalent to this skew tensor. Okay? And then we have here, in terms of components, we have this relationship which is well known. This is the Levi-Civita symbol, right? Permutation or alternating symbol. And we can, of course, invert that relationship, which is classical, and we have this. So this is a one-to-one relationship between this skew tensor of curvatures and twists and the associated axial vector. So later I will argue that this tensor here is constitutively important, so we will have an energy function, let's say, that depends on this in some way. And if you ask, how does this behave under a superposed rigid body motion, characterized by a uniform rotation over the entire body? So Q is independent of arc length. The embedded vectors transform in this way, and their arc length derivatives, which contain the physical information about curvature and twist, then transform this way. So R goes to QR, and this G goes to QG. We'll discuss more later. Okay, so then from the constitutive point of view, the important variable will be R transpose G, which is invariant under rotations. And it's really just the, you can think of as the pullback to the reference configuration of this skew tensor, which contains curvatures and twist. And this pullback is kind of a referential skew tensor, but because of the lack of distortion, the components are the same as those of W, just on a different basis, of course. And the associated axial vector, we'll call it kappa. Okay? And the components on the undeformed basis are the same as the components of the skew vector W of capital W. And they're related this way then. So this one is also invariant under rotations. So we can imagine this will be the constitutively relevant measure of strain in this model. And I repeat that this kappa then, two of its components are two bendings, curvatures, along the E2 and E3 directions. And kappa 1 along E1 is the twist of the cross-section. We can also look at the dynamics of this embedded triad. Small e is R, capital E. This can depend on time. This is like a material derivative holding arc length fixed. And we can associate this with a skew angular velocity or spin tensor, alpha. Okay, and an associated axial vector we call A. That describes the dynamics of the orientation of the cross-section and the tangent to the rod as well. Later on, I'll need a connection between this spin vector, like a vorticity vector in this model, and a relationship between that and these components of this curvature twist vector. A little bit of work is sufficient to establish this relationship. So the rate of change of our strain measures is related to the arc length derivative of this axial vector. And here's some interpretation. For example, from this relationship here, we can see that T1 prime, that's the curvature of the center line, is given by kappa 3 and kappa 2. So these are curvature components. E2 prime and E3 prime, these are the rates of change of the cross-sectional vectors as you move along the rod. See, so here's E2 is changing to this one, E3 is changing to this one, and the components here projected onto the cross-section are just kappa 1. So kappa 1 is the twist of the cross-section, the rate of twist. Okay, so I just said this. We can relate this to the fresshe basis by defining the principal normal in terms of the total curvature. The total curvature is just the norm of the projection of kappa onto the cross-section. And so we need some inertia terms also to do dynamics. the simplest thing to do to extract the form of the structure of the inertia terms is to write the position at a point in the cross-section in terms of position to some center line, which we've been using, R, and some cross-sectional components. It's like a Cartesian coordinate system with the generalization that the basis now can depend on arc length. And these cross-sectional coordinates x1 and x2 are also convected because there's no distortion in the cross-section. So a particle that had initially coordinates x2 and x3 in the cross-section have the same coordinates all the time under our assumptions. Okay, so let's fix the relationship between the position in the cross-section and the position of the center line by requiring that the center line position should be the average over the cross-section of the position in the cross-section at any arc length value s. Okay, so that imposes the requirement then that the average of the x's be 0. So we locate the r then at the geometric centroid of the cross-section. And then we can write the linear momentum over the entire body, a cylindrical portion of the body, like so, prismatic section of the body in the reference configuration. We can write that, we decompose that volume integral, and this is a mass per unit volume, as this iterated integral over the length and the cross-sectional area, like so. And we expand this and then use the fact that these x alpha are centroidal coordinates. And then with that, we define the mass per unit length, of course, in this sort of standard way as an exercise. And then we recover, we say that the total force acting on the rod will ignore any body forces. It's just the rate of change of the three-dimensional linear momentum, and that's the rate of change of this, okay? So we obtain the same linear momentum balance as before. But the exercise is useful in connection with the moment of momentum balance. So we have our same sector S1 to S2. Now we have some moments acting, forces as well. So here's the moment of momentum balance, the moments M1, M2, the moments of the forces balancing the moment of momentum in this cylinder. And we work this out and we have this simple result. The x's are convected, so they have no derivatives, time derivatives, and we have this. We use the fact that these integrate to 0 over the cross-section, and at any given cross-sectional S, the E alpha, the R, and so on do not depend on the cross-sectional coordinates, so we factor them out of the integral, etc., and we have this. So this is the form of the inertia, where this is the second moment of area, right, symmetric matrix. It turns out to be positive definite as well. So then this is the moment of momentum balance. Do the same as before. Let S2 approach S1 and assume everything is continuous. M2 will then approach the value M at S2. That approaches M at S1, etc. And then we have this relationship. This is 0 by, because Fs1 plus F1 is 0, and we have, we derive M1 is minus the function M at S1, come back into the original statement, and we have this, okay? And now we can write this as the integral of M prime, and so on, and this is the integral of R prime cross F plus R cross F prime. And R prime is the tangent, unit tangent to the rod. And so we're getting somewhere. Here's the integral statement of moment of momentum balance. Localize this because S1, S2 is an arbitrary interval. And this is the moment of momentum balance, linear momentum balance. So this is the structure of the inertia terms that are appropriate in this model. And then with these equations, one can imitate the program of conventional continuum mechanics, if you like, and form a work energy identity. So let V be the velocity. Take a scalar product of the equation of motion with the velocity, integrate, and so on. V prime is then given by the time derivative of the unit tangent, which we know is, we had EI dot is A cross EI. This is a special case of that for I equal 1, and so on. So this is a power term. We write it this way. Then we import the moment of momentum balance, which involves T cross F and the moment, like so. And we derive this energy identity, time rate of change of kinetic energy. Here's another kinetic energy type term. It's not clear immediately that it has that structure. We want to write it as the time derivative of something. This term then looks like a stress power term, and this is the power of the applied forces, force and moment. Okay? So S here is the analog of the stress power in continuum mechanics. The only thing interesting about it is it involves only the moment in this theory. It does not involve the force, because in this structure, in this theory, the force generates no energy. Because the force in this theory is really a Lagrange multiplier against the severe kinematic constraints imposed in the theory, inextensibility and unshearability of the cross-section of vectors. So really the force here is a Lagrange multiplier, does not participate in the energetic balance. And we can show with a little bit of labor that this funny term in the energy balance is really just the rotatory inertia, like so. So now we've converted it to a derivative, and so now we have the standard power identity, where this is now the kinetic energy, including so-called rotatory inertia terms, the stress power, the power of the applied forces. And one can show that this object here is a positive definite function of the spin vector A. That's just an exercise. I won't stop for that. Okay, so that guarantees that the kinetic energy is positive definite, and the variables are the velocity and the angular velocity. So let's do elasticity. So assume that there is a potential U such that the stress power is the time derivative of U in any motion. And let's further assume that there's an energy density W such that U is the integral of W. Okay? So this U would be like a strain energy per unit length. So then we can write this equation in this form and localize it to obtain this rate of change of energy is balanced by the stress power density. So this is where we will extract elastic constitutive equations for the rod. So let's assume, as I mentioned before, that the strain energy depends on G. G is R prime, which we like this because R prime contains information about curvature and twist. So somehow we expect the energy to depend on these variables. We could extract this assumption from a three-dimensional derivation, but let's stay one-dimensional for now. So this is a kind of a priori constitutive assumption we can make. Impose invariance of this under rotations if we want to, objectivity essentially, and we find that the energy must depend, the energy let's see, depends on G via this omega, this referential skew tensor that we talked about before. And that's equivalent to its axial vector kappa. Okay? So that ensures that we have this so-called objectivity condition satisfied. And so then we extract from the localized power or stress power equation, we extract this equation here, where M(I)EI is the moment on the cross section, and then we have the constitutive equations, the moment curvature and moment twist relationship. Okay, so then with this, we're constructing a Hamiltonian system essentially, ultimately. So we have this power balance, the rate of change of the time rate of change of the kinetic plus strain energy is equal to the power, like so. And as a special case then, this applies over the entire rod. And the power is just the power of the applied forces at the ends of the cross sections and moments. we want to know, actually it's an interesting issue, under what conditions can this power itself be the time derivative of something? That something would then be a potential energy for the loads. And in the case of rods, it's not an obvious issue. For example, if F applied to the end of the rod is constant, fixed like a dead load, then we know this part is conservative. It can be written as the time derivative of some scalar. But if the moment is prescribed as a dead moment, it turns out, interestingly, that this is not conservative. So there's a little bit of an interesting literature on the possibility of having conservative loads in a Kirchhoff rod theory. It's not so trivial. So let's focus attention on a very simple example. So we have an initially straight rod clamped at one end. That means the position there is prescribed and the cross-sectional vectors are also assigned. At the other end, the rod is free to slide horizontally under the influence of a fixed force. Okay? So the velocity at the left end is 0. The position at the right end is along the horizontal direction. The length can vary. Its velocity then is the time derivative of the length, and the power of the force with a prescribed force is just the time derivative of some quantity, so that quantity is essentially the potential energy. And we do something similar for the cross-sectional vectors at the end. We suppose they're fixed, so they don't change. Over here, we suppose they're also fixed into this cement block here. That means this spin vector has to vanish at both ends in this simple example. So that defines the class of kinematically possible configurations. So in this case, because A is 0, the contribution of the moments at the ends to the power disappears, and the power reduces to this. And now we have an example of a conservative problem where this Hamiltonian is conserved, the total system energy, and this total energy consists of the strain energy and the potential energy, like so. So we're imitating the program of the finite dimensional conservative problem. Okay, so we see the structure is preserved. It's a Hamiltonian dynamical system. So we imagine that we might be able to generalize the Lagrange-Dirichlet or Lyapunov theorem to this problem to prove stability, and also generalize the Chetaev theorems to prove instability, possibly. So we would like to attempt to carry out this program. Okay?
Sorry.
Yeah.
You said something which made me
Unhappy?
Yeah. Sorry, not conservative.
Yeah.
So if you write an energy depending on position and rotation of the dead, of the end.
Yeah. Here.
Here,
this term here. Yeah. So this thing, in the conservative case, the power is the time derivative of some potential. We could just construct an example in which we have this situation.
So
but yeah.
Depending on the position of the section and on the rotation of the
You will find then that you cannot sustain that case with a fixed moment.
So it is not an exact form.
That's right. When M is prescribed, just like the force is prescribed, so no matter what the configuration, the moment is a fixed vector, then you will not have...
So you have to change the forces.
To have a dead load, A is related to the rate of change of the orientation. There's a cross product with the embedded vectors. So the combination must be, it's the EI cross some, so M, if M has the structure, let's say you have some 3 fixed vectors, small m sub I. You could have a situation in which small m sub I is fixed, then the moment must be small EI cross small mi. Therefore it's not fixed because the small EIs are changing with the configuration. So that's not a dead moment. So the dead moment is not a conservative problem. It's a counterintuitive, but it's interesting.
Unexpected.
Yeah, exactly. Okay, so...
You linearize, it is possible.
I don't know. I don't think so.
So what we are doing? when we give exercise to students, students, we are asking them to study conservative.
Here's a conservative case. So you put the rod in a sleeve, and you allow rotational motion in the sleeve without changing the orientation of the rod. You can now prescribe a constant twisting moment, right? And that is a conservative problem. Things like that. So you have to be careful. Yeah, a dead moment is really like a follower force, but of course one has to be careful because one can have an actual force as a follower force. That's not conservative either, right? So yes, I mean in that problem normally we prescribe zero moment at the end, and we have a follower force. Zero works, but the follower force does not work. So we can construct some interesting trivially construct some interesting non-conservative problems in this case. Okay? So we want to say something about the constitutive relations. The strain energy per unit length as a function of these curvatures and twist. Let's suppose that the fiber or the rod is thin in comparison to, say, the minimum radius of curvature in a deformed configuration. So that would mean the dimensionless curvatures, non-dimensionalized by the cross-sectional dimension, are very small. And that means we can estimate the strain energy for small values of the non-dimensional kappa vector. And here we have a Taylor expansion out to quadratic order. And these are the moment and twisting components in the reference configuration. And we have here a stiffness then, elastic moduli. So if we suppose the reference configuration is in equilibrium under no moments or loads, the straight prismatic untwisted configuration, then equilibrium tells us this and this. E1 is the tangent initially. And so the force at any cross-section is equal to the force at one end, either end, which we take to be zero if the unloaded configuration is in equilibrium. The moment, then this is zero, and then the moment on any cross-section is equal to its boundary values, which are also zero. So when there's no curvature, the linear term in the strain energy function is zero by assumption, and the leading order term is quadratic. Okay? This is not a small deformation assumption. In linear elasticity, you do the same thing where you assume the strains are small, but they're a priori non-dimensional. Here we're using a dimensional analysis. Right? The non-dimensional curvatures scaled by the cross-section dimensions are small even in a finite deformation, so that even in a finite deformation we can justify the quadratic energy, which is why in the Elastica theory or Kirchhoff theory classically you always see a quadratic energy even though you're looking at very large deformations. So in the simplest case, say an isotropic material and a circular cross-section, then this rod strain energy will be transversely isotropic about the tangent, and we'll have this structure. So it will be a function of an isotropic function of the projection of kappa onto the cross-section, like so, the classical flexural stiffness, E times I, where I is the second moment of area of the cross-section, G shear modulus, J the polar moment of the cross-section gives you the twisting terms, and then you can extract the moduli in this way in terms of these are Kronecker deltas, so very simple. So this classical standard constitutive relation, and it's something we can use for our discussion here. Okay. Okay. So with that we can extract the moments as C times kappa, and we have the twisting and bending moments here. The EI contributes to the bending, as you expect, and GJ is the twist along the tangent, right? Twisting moment in the direction of the tangent. And we can simplify further in this special case by observing that kappa 1, this vector here, is just this, which is E1 cross E1 prime, the tangent cross its derivative. So we have this kind of compact form of the constitutive equation, T cross T prime, kappa 1 along T. So these two terms are orthogonal to each other, right? T is in the tangent, T cross T prime then is in the cross section. It gives you bending moments, and the last one is the twisting moment. Okay, so when we were talking about finite dimensional systems, we saw that the linearized theory was of relevance in the analysis. So before we proceed to the stability theorem, let's quickly look at the linear theory. So suppose we have an equilibrium configuration, and then a small perturbation of it, a new configuration, in which the position is the equilibrium position plus a small change, and the cross-sectional vectors are what they were in this configuration plus a small change. So the hat will be the small, the epsilon times a hat, or epsilon times something, will be the small perturbation, and we're going to just extract the leading order terms in epsilon, so we linearize. We'll assume the same for the forces and moments. This comes from the constitutive equations, but this is an additional assumption because, as I mentioned, the force is not given constitutively in this theory, right? If you do elementary beam bending theory, you get the force, or the shear force on a cross-section, let's say, purely from equilibrium considerations, never from constitutive equations. So you maybe perhaps believe that this is a Lagrange multiplier. So the assumption that a linear perturbation in the kinematics yields a linear perturbation in the Lagrange multiplier, that's really an assumption we have to verify after the fact. So we demand that this motion tilde should satisfy the equations of motion, etc. And we can linearize. So at equilibrium, this configuration is an equilibrium with no inertia, so the force in that configuration is uniform. Put that back in to this equation. The leading order term then is just the linearized equation of linear momentum balance. The moment of momentum balance is a bit more complex. That involves this inertia term here. We have to linearize it. A priori, we extract easily the leading term. This is the initial equilibrium, let's say, and this is the small perturbation. And we have our, in equilibrium, we have this expression. We use that, and then we obtain this linearized equation of motion. Excuse me. So this is the perturbation in the moment, perturbation in the force, perturbation in the tangent, perturbation in the embedded vectors. So, what is the structure of these perturbation in the embedded vectors? That's like this. It's essentially the leading order term in a Taylor expansion with respect to epsilon. But these e's are rotations times the initial e's. So this derivative will bring a skew tensor, and we say b tilde is its associated axial vector. So this is a small rotation and twist of the cross-section. So the perturbation and the e's have this structure. Some vector, unknown, cross the e's. And from that we can compute the linearized strain, the linearization of the strain measure, call it kappa hat, in this way. And we conclude ultimately that the linearized strain is just related to the derivative of this. This is like a strain measure then, the derivative with respect to arc length. Okay. And let's see if that's interesting or not. Okay, so this is not so interesting. We have the linearized constitutive equation then, like so. T hat is b cross t. T is r prime. The increment of it is the prime of r, of the increment of r, but the increment of r is u. So t hat is the arc length derivative of the small displacement. And the twist here, like so. So let's look at a circular cross-section, for example. Take our equilibrium, our initial equilibrium configuration to be a straight rod. So r is a linear function of arc length along a fixed direction E1, and all the e's are equal to their reference values. And we'll have a force which is purely compressive, so that it satisfies equilibrium, right, with the F equal a constant. So this is the straight, unbent, untwisted configuration, which we can maintain in equilibrium for any force F. Okay? From the equilibrium equation for that configuration, here is F is along E1, so the moment is uniform along the fiber, therefore equal to its boundary value. We'll put 0 here. We have this. In particular, then, we can have no twist. A priori, we have no flexure, so we also have no twist. And we've satisfied the equilibrium equations for any value of the force. Of course, ultimately, we're interested in the stability of that configuration. The linearized equations with respect to that configuration look like this vector equation. M involves a small twist and a small flexure, which is related to the second derivatives of the displacement. We put that in the moment of momentum balance, and we have something like this. This is 2 time derivatives of this B vector we mentioned before. Okay, so that we can decouple that equation. If we project it onto the tangent, we get this equation. And ultimately, we get this equation for the torsional motion, the wave equation for torsional waves. Okay, so that's very familiar to everyone. And the remaining part of the previous vector equation then just describes the flexural part. Okay? And with a little bit of effort, not so interesting, we can convert that into this vector equation. And U now has components. We're interested in the U2 and U3 because we're taking a cross product with E1. Okay? And for either U2 or U3, then the 2 equations are identical. And this gives you the transverse motion of the linearized equation for the transverse motion of the rod. And in this simple case, we were looking at the equations decouple. Professor Luongo already mentioned that situation. So let's look at a pinned rod, pinned at this end, pinned at this end. That means no moments applied at the ends. And this position is free to move back and forth. Horizontally, this one is fixed. And let's look at the case no load at all. And look at the motions, the possible motions. So the boundary conditions here, let's suppose there's no displacement in the linear theory, no moments. So that means the second derivative of either U2 or U3 is 0 at the ends. We can impose an initial condition. Let's say we hold the rod initially in the sinusoidal configuration, n is an integer, c is a constant, and suppose we hold it with 0 initial velocity. Then we can show easily that the solution to the equation of motion has this form, cosine omega nt. We find omega n by putting it into the equations. What we find is this rotatory inertia term enters through something called the radius of gyration. The only thing interesting about it is it is of order thickness squared. This is thickness to the 4th, thickness squared. And so on. So we compute then these frequencies, the squared frequencies, in this manner, where n is the chosen mode. Okay? And this is order h squared, as I mentioned. So for n small means the wavelength of the initial disturbance is small, or sorry, is long, and we're in the low frequency regime for n small. And we can see then that this term has a negligible effect on the frequency. That's a classic result which people use to justify the suppression of the rotatory inertia term in the classical equations for rod dynamics, at least in the linear theory. It's dangerous to make such arguments in the nonlinear theory. Okay? So let's say now we need a way to measure the size of the motion. Here's a norm we can use, the max norm, local max norm of the disturbance, which is the motion, and it's the maximum of the velocity as well. And then at the initial time, we have this, the value of this norm is just the constant c that we put into the initial condition. So remember now we're just looking at the motions of the unloaded, unforced rod, okay? At time t, our motion gives us this measure, d, okay, where omega n here satisfies this. So notice that for large n, which is a highly curved oscillating initial condition, omega approaches this value asymptotically, and that means the size of the disturbance, because of this omega term, the size of the disturbance, even though the initial disturbance had a fixed size, for a large enough n, we can make the size of the disturbance grow without bound. So we have a kind of curious situation here, where if we use this as the measure of the size of the disturbance, as a surrogate for the norm that we were using in finite dimensions, then the undeformed rod, which is unloaded, is unstable with respect to this particular measure of the size of the disturbance. So we see immediately we can have some very pathological conclusions. This is, physically we don't expect this, right? We have the undeformed rod supported in some way, and yet the undeformed rod is unstable with respect to this measure. So clearly we need to use a measure that makes sense for the physics of the problem. So if we use the wrong norm, we always deduce instability. So we need to have a kind of a concept of size or norm of the disturbance that fits, is natural for the physics. What can we do for that? Well, let's look at the energy. The energy of the undeformed rod as in its motion, well, after the small motion, the sinusoidal motion, looks like this. So for plane bending we have this, which is the situation we're looking at. So let's suppose we have either U2 or U3 because they're decoupled. So we have the classical energy that you know from classical rod theory, okay? Excuse me. And the kinetic energy also, we can do a little bit of work, which is not interesting, to conclude that the kinetic energy in this flexural mode, here's the rotatory inertia term again, and the conventional kinetic energy term. So the Hamiltonian for our small motion looks like this. And using the linearized equations, of course, we're going to have a conserved Hamiltonian. There's no forcing applied. So if you have a motion with zero initial velocity, the Hamiltonian will be equal to its initial value, which is just the potential energy, the strain energy now, because there's no load. So it's just the energy of the initial condition. So we put in the initial condition and we have this. So this is the measure we were using before, which was just, remember, the initial condition had a measure of C, which we can control. So we have a situation in which the initial condition is a positive definite function of the measure that we've chosen. So it sounds like we're satisfying some conditions of a Lyapunov type theorem, right, which rested on the assumption of a positive definite energy with respect to a chosen measure. Yet we've just constructed an example in which the same measure blows up at subsequent times. So we can, even though we have a positive definite strain energy with respect to this measure for the initial condition, the disturbance becomes unbounded using that measure. Okay. Yeah.
Excuse me.
Yeah.
What happens is that if you have a lot of
high frequency, short wavelength.
The velocity goes.
In this measure, the distance, this norm, explodes. So it's the wrong way to measure the size.
The Lagrange norm is not good.
Right. So, but we're going to fix it.
So you will choose energy.
Yeah. Right. Exactly. So one can find similar examples in the context of 3D elasticity. Here's an old paper. Around this time, this era, in the early 60s, people were worried a lot about this. You can make even in linear elasticity, you can conclude in the same way that a 3D linearly elastic body is always unstable. I hand it to you, no loads, nothing. I support it properly. It's unstable because I've used a stupid norm to measure the size of the disturbance.
And I thought that this could be a clever example.
Yeah.
To tell that norms are dangerous.
Yeah, exactly. So the whole point of this brief discussion is that the norms can be dangerous if you don't choose them carefully. There's a classic review article by Knops and Wilkes in the Handbook der Physik series, which everyone interested in elastic stability should read carefully. It's Knops and Wilkes, about 1973, but it remains a but they discuss this pathological example and make the case. They illustrate that we have to be careful. Yeah, that's right. Green and Shield, the engineers. So, so what we have is we have an energy that's zero at the underlying equilibrium, the straight configuration. Right? The energy is zero. It's positive definite with respect to this measure, but we can construct a sequence of configurations whose measure tends to zero, but for which the limit of the sequence of energies is not zero. In other words, what we have with respect to this chosen measure is a situation in which the energy is not continuous at the zero state. And remember back to the Lagrange-Dirichlet theorem, the continuity condition was crucial in making the proof of stability. So in fact this energy is not continuous with respect to this measure. We can see that easily. So here's this is another reason why this is a bad measure. Let's construct a sequence of displacements like so, with n is the index for the sequence. So this, according to this measure, then this is the size 1 over n, so the size goes to 0 for large n, okay? But the energies evaluated on the sequence blow up for large n. So even though the measure is tending to 0, the energies blow up. So, but at 0, we have 0, right? You put in 0 for we have integral of u double prime squared, put in u equals 0, we have 0. So the energy is not continuous with respect to this measure. So there's no possibility of imitating the Lagrange-Dirichlet theorem in this case for this measure. Let's see if we can possibly find a way to extend the Lagrange-Dirichlet theorem to this case. We already know we have to be careful with the choice of norm. We have to have a continuity condition satisfied with respect to that choice of norm, and so on. So here's our equilibrium configuration, the perturbed configuration. Kinetic energy is repeated. If we'll have a Hamiltonian system, if the loads are conservative, so we have a load potential, and so on. Okay. Some nice papers, one by Coiter, and later, here in Italy, one by Como and Grimaldi, an excellent paper, which establishes the Lyapunov theorem, essentially for systems like this. 1994, so that's very recent. So this was an open problem until not very long ago. Okay, so let's try to carry out the program of Lagrange-Dirichlet. So we'll look at the change in energy away from an equilibrium configuration, call that delta E. And R tilde, E tilde can be written in terms of the perturbations, change in R, change in E, like so. And our state then, our perturbation away from equilibrium consists of the array delta R, delta EI. So the change in energy away from our equilibrium state can be written as some functional of this x. Okay? And when x is 0, by definition we get 0. Okay? So we're casting the problem in a form suitable for the Lagrange-Dirichlet theorem. The kinetic energy can be written in the same way as some functional of x dot, which vanishes when x dot is 0. There's no velocities. And the total energy of the tilde motion associated with this motion can be written this way. Here's the energy plus the new energy minus this energy, so it's the same as this. And this energy is just the Hamiltonian in the equilibrium configuration, because there's no kinetic energy there. So we say script h, cursive h, is the difference in the Hamiltonians, and that can be written as a functional of y, which is the state xx dot. Okay? And the equation of motion guarantees for this Hamiltonian system that this is conserved in time. Okay. Okay, so we want to determine a norm. We don't know what it looks like yet. Norm x, norm of the disturbance. Okay? And having norm x, we will seek the form of this norm. But once we have such a form, we will define norm y is xx dot, by this formula. Okay? So this is something positive definite, this will be positive definite, and we'll get then y positive definite. So at this stage we don't know the structure of this norm yet. We don't know the structure of the appropriate norm. We're going to discuss that. Okay. But we can, having this as yet undetermined norm, we can then state the Lagrange, or the Lyapunov stability definition. So our equilibrium state, the x is the perturbations now, so the equilibrium state corresponds to 0 perturbation, is Lyapunov stable as before, if when we prescribe epsilon, there is a delta such that a delta bound on the initial condition implies an epsilon bound on the motion, the disturbance for all time, let's say. Now, in order to imitate the program of Lagrange-Dirichlet for finite dimensional systems, we have to add some hypotheses on this energy, potential energy. Remember, in the finite dimensional case, we had a continuity condition which we guaranteed as part of the hypotheses in the Lyapunov theorem. We have to assume the same here. Our energy functional is continuous with respect to the norm to be chosen at x equals 0. So that the limit of the energy as x tends to 0 in norm is equal to its value at 0, which is 0 by construction. The next assumption we made in Lagrange-Dirichlet was positive definiteness of the energy. This is technically more difficult here, for reasons we'll discuss later, but for now we can ensure positive definiteness by the following statement, that in some ball enclosing the equilibrium, the energy is bounded below by a strictly increasing function which vanishes only at x equals 0. This guarantees the positive definiteness condition which we will need. Okay? Now, in the finite dimensional case, all we had to do was say epsilon is strictly positive. Here we will see in a moment that's not enough. Epsilon must be bounded below by a positive increasing function that's 0 only at the origin. Okay, so let's next make the following construction. Let's fix an epsilon in this ball, a ball within this k-ball, and look at the set of configurations that lie on that epsilon sphere. But this is a function space now, it's not a finite dimensional space. What we want to show is that the infimum in this set of the Hamiltonian is strictly positive. In the finite dimensional case, we could use continuity to say that the infimum is achieved and it's actually a minimum. Right? We don't have that property here because in function space this is not a compact set anymore. Okay? So we have major technical challenges ahead of us to do things with a level of rigor that we would like that we would like to have in the finite dimensional case. So let's pick an alpha in this interval between 0 and epsilon and divide this unit sphere, or this epsilon sphere, into two parts. X between 0 and alpha, strictly, and x between alpha and epsilon. So that, remember, the kinetic energy then, we're on this epsilon sphere where the squared norm of y is equal to epsilon squared. So for either subset of this epsilon sphere, we have this statement. Okay? For y in A1, we have this, and so this statement yields this inequality. So the kinetic energy in this part of the epsilon sphere is strictly positive. Then the Hamiltonian is this plus the potential energy, which by assumption is bounded below by this increasing function. It's increasing, so because x is greater than 0, norm x, we have this inequality, and this is 0. So the Hamiltonian is bounded below by k, which is strictly positive. Okay? In the remaining part of this epsilon sphere, we have norm x bounded below by alpha, a fixed constant. So the potential energy, which is bounded below like so, is bounded, this is an increasing function. So this is bounded below by phi at alpha, which is non-zero, therefore this is strictly positive. So the total Hamiltonian, which is this is positive, is bounded below by epsilon, which is bounded below by this strictly positive number. So what we can say is that for y in this epsilon sphere, the Hamiltonian is bounded below by a strictly positive number. So its infimum on that epsilon sphere, we'll call it h star, is a strictly positive number. Okay? So this is essential for what we do later. The infimum here, although it's not a minimum, the minimum is not achieved, no, the infimum is not achieved, in other words, but the infimum is strictly positive. We can also claim that the Hamiltonian is continuous with respect to the norm to be found, since the norm tending to 0 implies that the kinetic energy tends to 0 from the way we define the norm. Kinetic and the norm of x simultaneously tend to 0 because they're both positive definite. So this limit is the same as the limit of epsilon, which we claimed as 0 because we've assumed continuity of epsilon with respect to this norm. Okay? With respect to x in this norm. Okay? We have to verify this, but for now we can make the assumption, which we'll have to choose a norm such that this can be achieved later on. So we have this continuity condition of h with respect to y in this yet to be determined norm. So we have this, right? So a delta bound on y implies that we can make h as small as we wish, in particular smaller than h star. So now we can, with all these hypotheses in place, which we of course must construct a structure which gives these hypotheses, we can pick an initial condition, and here we're on our rod with the parameter as arc length, such that the initial condition, which consists of position and velocity, is bounded by delta. So then the initial condition satisfies this inequality. So at any given time, the Hamiltonian is conserved, therefore equal to its initial value. So at any time, the Hamiltonian is bounded above by this h star. This means that the motion can never reach this epsilon sphere, because if it does, if y belongs to, at any time, belongs to the epsilon sphere, then it satisfies this inequality because h star was the infimum on that sphere, a strictly positive number. So if this happens, this is an impossibility because for any time h remains below that value. So the assumption that y reaches the epsilon sphere, in other words, we're escaping the neighborhood of the epsilon neighborhood of the origin, yields a contradiction. So it can never happen. Y remains bounded by epsilon. And so under these hypotheses, the equilibrium is stable. Now the hard part begins. We have to construct a norm which satisfies all these criteria. Okay.
Sorry,
Yeah.
who did this first?
I would say, so the problem was known for a long time, that it's difficult to enforce the continuity. There was the problem of the non-compactness of this epsilon sphere and so on. I would say in this context probably Como and Grimaldi were the first to do an explicit construction. So, which reminds me to remind you all, Italian mechanics is the best in the world, Italian theoretical mechanics. So you young people are responsible to maintain this national tradition for the benefit of Western civilization, right? As goes mechanics, so goes the nation, right? It's true, I think, right? So the path to prosperity is via mechanics, I believe. It sounds silly, but I believe it's actually true.
This is a Neapolitan school.
Yeah, okay. No, but this actually, when I was making this course to deliver at Berkeley, I dug deeply into the Italian literature on this subject. It's a very good literature. Coiter is outside of Italy, Coiter was the #1 person in stability in the world, I think. He knew these things, and I'll mention him later.
By the way, I should give you the papers by Salvador.
Okay.
Because Como and Grimaldi are pupils of
Okay.
this specialist in stability. Salvador was a pupil of Levi.
Wonderful. Yeah. So no surprises, right? So, but I'm essentially following the Como-Grimaldi program. The theory is somewhat different. They used a priori simpler version of the theory, but so what? But this is something here very important. We had an assumption that the potential energy is bounded below by a strictly increasing function. That is sufficient, that guarantees the positive definiteness condition that we needed. In finite dimensions, we simply had to say that the potential energy is positive definite in this sense. For x not 0, the potential energy is strictly positive. But then, all we can say is that the infimum of the Hamiltonian on this epsilon sphere, the infimum could be 0. Right? Because this set is not compact in function space. So even though we have this, even if we assume this, we cannot guarantee that the infimum of the energy is strictly positive. If we don't have strictly positive, if you look back at the finite dimensional version of the theorem, the argument does not hold. We need a strict positivity here so that we can go below, we can use continuity to choose states y that are below that strictly positive number. Without compactness of this set, we don't have compactness, we cannot claim that this is true. So the infimum might be 0, and then we cannot implement the details of the Lagrange-Dirichlet theorem. Okay, so that's why we replace this inequality that we had in the finite dimensional case by the assumption that epsilon is bounded below by a strictly increasing function of norm x. Okay, so we have to verify that lower bound in an actual problem in order to do a rigorous Lagrange-Dirichlet theorem. Okay, now the problem a la Como-Grimaldi is to fulfill all of the foregoing hypotheses. Continuity of the energy with respect to choose the norm, so that we have continuity of the energy with respect to that norm. Okay, and then verify the lower bound. The epsilon should be greater than or equal to some phi, some function phi that we have to choose. In finite dimensions, we assured the continuity condition by assuming that the energy was differentiable. Right? Differentiable functions are continuous. In this context, the appropriate analog of that is fresshe differentiability of the energy. Okay? So fresshe differentiability of the functional. So this is just a generalization of the usual notion of derivatives in finite dimensions. Here, fresshe differentiability means, for example, we have this expansion. let's say it's twice fresshe differentiable. Capital D is the fresshe differential. So then we can have a fresshe expansion of the energy analogous to a Taylor expansion, but not the same thing. Epsilon at any x is epsilon at 0, the first fresshe differential, the second, and a remainder. So these are the first and second fresshe differentials. And the remainder is small o of norm x squared, where the norm has to be chosen appropriately. Okay? And so what do we mean by fresshe differentiable? It means that there's a bounded linear operator, or linear functional D, the fresshe differential, such that the usual definition of a derivative is satisfied in this chosen norm. Okay? Fresshe differentiability involves intimately the definition of the norm you use. In finite dimensions it doesn't matter because we have norm equivalence. Okay? And this linear functional should be linear and also bounded. We have to impose this separately. In finite dimensions, linear operators are always bounded. In a function space, it's not so. So we impose boundedness as part of the hypothesis. Okay? So we need to show also this is a bounded operator. So there's some constant A such that this is true. Another indication of the complexities that face us if we want to have a rigorous characterization of stability. Okay, so D epsilon is a linear operator. We emphasize that by writing it in this form, where x is explicit here, and A is then called the fresshe derivative. We'll use this notation at x equals 0. Okay? So it's the state x equals 0 that characterizes the structure of the fresshe derivative, and then the argument is x. Okay. And from the boundedness requirement that we impose, we must verify. We can say that A is bounded below by the supremum of this ratio. This is the absolute value of the fresshe differential. So this is a scalar. We can take its absolute value. And this is defined to be the norm then of this fresshe derivative. So the norm of the fresshe differential, the absolute value of it, is bounded above by the norm of this derivative times the norm of x. So by assumption, there's a constant A which gives an upper bound to this norm of the fresshe derivative. This is something we must verify later in any particular problem. So this is a linear operation, so this definition of the norm is equivalent to this one, where U is now on the unit sphere in this function space. And then we can show, just as in finite dimensions we know that a differentiable function is continuous, we can show that a fresshe differentiable function is also continuous. So here we have, if there's one fresshe derivative, say at 0, then we have this expansion with the remainder that's small o norm x. Then this is enough to show that epsilon is continuous at x equals 0, and that's easy to show when the proof is right here. Right? Look at the difference between epsilon at x and epsilon at 0. That's given by this, bounded above by this. Use linearity to factor out norm x, and we have this. This is fixed constant. Send x to 0, then this tends to 0. So we have a continuous function at x equals 0, and in fact at any x. Okay. Some nice references. Weinberg, a very famous reference on nonlinear operators. A less well-known one that's of use in the computational community. Sometimes this is interest in the computational community. I think this just proves continuity at any x, so we skip it. Okay. In the same way, we can say that this functional epsilon, the energy, the potential energy, is twice fresshe differentiable, say at x equals 0. If there's a first fresshe derivative that we've just constructed, and also if there's a second derivative in that, such that that fresshe expansion is true, where the second fresshe differential is quadratic, homogeneous quadratic, and also bounded above by the squared norm of x. Okay? The vanishing of the first fresshe derivative is really just the virtual work principle. This is equilibrium, or it implies equilibrium. Even in this case, so at equilibrium, the fresshe expansion begins at second order with the second order fresshe differential. And even in this case, we have continuity of x at the origin. So the existence of the second fresshe differential ensures that the energy is continuous at the origin again. Okay? The first fresshe differential vanishes at that equilibrium. So we need continuity as part of the Lagrange-Dirichlet theorem. Sufficient for that is the existence of a second fresshe differential of the energy function. So we will try to find conditions under which the second fresshe differential exists. Okay. Let's now look at the unit sphere in this function space. We will attempt the following procedure. We're going to try to find conditions of loading which are involved in the energy functional, such that the infimum of the second fresshe differential on the unit sphere is strictly positive. Some lambda that we choose is strictly positive. Okay? The infimum, this will not be a minimum because this is not a compact set. So this is the analog of the assumption that the second variation is strictly positive. Okay? Here we need it. This is the analog of that. Okay, so that means this is true, that for any x, the second fresshe differential is bounded below by this form here. That guarantees then, as we'll see, the positive definiteness condition, the bounded from below condition for the energy. So we will attempt to find, to satisfy this, fulfill this condition. So then the energy expansion in the neighborhood of the equilibrium looks like this. Because we have equilibrium, the first fresshe differential is 0. And we have this inequality, and this continued inequality. And because of continuity now, we can choose norm x small enough to make this smaller than any desired number. Let's pick 1/2 lambda as an example. And then we can guarantee that the energy is bounded below. So this is our phi of norm x, 1/2 lambda norm x squared. And we will try to ensure we can do this with lambda positive. So this gives us our positive definiteness condition. So this lower bound on the second fresshe differential on the unit sphere, positive lower bound, guarantees that in a small enough neighborhood we have one of the hypotheses of the Lagrange-Dirichlet theorem satisfied.
If not missed, not yet defined.
Not yet defined the norm. I'm about to do that. If we can, this is the program we want to carry out, and now we must find the norm that allows us to do so.
So the
killer is the norm. This can really, we've already seen that a naive choice of norm will destroy this program. We don't have continuity, we don't have a lower bound, etc. So the problem is to find the norm, as you say, for our given system, such that this program, all this story can be implemented so that we can fulfill these hypotheses. If we can do so, then the hypotheses of the Lagrange-Dirichlet or Lyapunov theorem are satisfied, and we then have stability with respect to this norm. Okay? If we choose this correctly, we guarantee stability. Because this is the exact analog of the second variation, positivity of the second variation being sufficient for stability in the finite dimensional system. But technically it's much more challenging. So here is the idea of Como and Grimaldi. We saw before that a stupid choice of norm will yield the conclusion that even the undeformed configuration of a rod is unstable. This is not physically something that we can live with, right? If that configuration is unstable, then we can never find any stable configuration. So we want a choice of norm for which some problems can be stable, otherwise this is a meaningless subject, right? So the Common-Grimaldi idea is, suppose that the unloaded body, the so-called natural state of the body, is supposed to be in equilibrium and supported in a suitable way to forbid rigid body motions. Suppose this can be stable. So this is the classical elasticity situation, right? If you have in classical elasticity, for small perturbations of an unloaded, say, natural state of the body, we have stability. Stability is an issue that never arises in linear elasticity for this reason. Okay, so their idea was to suppose, let's choose a norm such that this configuration is judged to be stable. Notice that for deformations from this natural state, and this natural state is different from a loaded equilibrium state. This is an unloaded equilibrium state. For deformations away from this natural state, our potential energy reduces to energy sub natural state, energy sub n. And if it, as a special case then, it should be twice fresshe differentiable to meet the foregoing program, so that the remainder is small o norm x squared, and the second fresshe differential relative to the natural state with no loads should be bounded above by this quadratic term for some positive Bn. So from the foregoing we can say that the natural state will be stable if the second variation is positive definite. In our context that means the second fresshe differential evaluated at the natural state is bounded below in this way for some positive number lambda n, which we can find somehow in principle. We could find this lambda n. We could find the best constant, say the least constant, says this is true. Okay? What's good about what's useful about this epsilon n relative to this natural state is it's intrinsic to the system we're studying. It's independent of the loads. It's independent of what you do to the system. It's a property only of the system itself, independent of the loading. Okay? So this is an attractive feature. And in fact, this is a very messy slide. Let's introduce this triple bar norm. This is Miquelin's energy norm, so-called, which is just twice the second fresshe differential relative to the natural state. Then from the foregoing we can say that it's bounded below by 2 square root of lambda n, which is a positive number we can find in principle. But the second fresshe differential is bounded above also by Bn norm x squared. So the norm itself, this triple bar norm, is bounded above by some constant times the norm we might choose to affect this program, to meet all these sufficient conditions. So it's bounded below by any other norm we might choose that would fulfill these criteria, and bounded above by some constant times the same norm that we might choose to fulfill all of these criteria. So effectively, this energy norm is equivalent to any other norm that can be chosen to meet the foregoing hypotheses. So of course we don't have norm equivalence in general, but if you can find a norm, ordinary norm x, to meet all of the foregoing criteria, to meet all of the foregoing hypotheses, then it will be equivalent to this so-called energy norm. And there's a beautiful book by Miquelin discussing the uses of this energy norm to prove various things about quadratic variational problems. So, in fact, we can show that this triple bar norm is in fact a norm. So it's equivalent to any other one that you could choose which would fulfill the hypotheses of the Lagrange-Dirichlet theorem. And because it's easily computed for the physical system at hand, it's of course a natural choice.
So you able to say if I have I calculate its
fresshe differentials. And if you can...
norm.
Yeah, I know. But let's say you need the norm, right? This is the point I was just making, right? So we have yet to choose the norm. Norm x. If we can verify the hypotheses that we've just mentioned, which guarantee Lyapunov stability with respect to that chosen norm, it will be equivalent to this energy norm. So any norm you might choose will fulfill the condition of norm equivalence to this energy norm.
Simply because the second derivative
Yeah, because we
on the norm.
right, exactly. Well, yeah, but we're going to use the second derivative at the natural state as the norm itself, because automatically, if all those hypotheses are met at the natural state, then that will produce something that is equivalent to any other norm we might choose to affect the same program. And this is easy to compute. We might as well use it. Okay. So we'll use this triple bar norm, Miklin's energy norm, and attempt then what we need to do then is to show that epsilon is twice, the energy from some loaded equilibrium state is twice fresshe differentiable with respect to this energy norm, and bounded below in this manner for some strictly positive constant lambda. If we can do this, then we guarantee that all of the criteria, all of the conditions of the Lagrange-Dirichlet theorem are satisfied for that norm, and then we can prove stability for that with respect to that norm. So it's a norm that's naturally suggested by the physics and the structure of the Lagrange-Dirichlet theorem. And of course, if you use the wrong norm, then you will conclude instability. That would render the whole subject vacuous. There would be no such thing as a stable system, and that would be absurd. Now, how do you compute fresshe differentials? Well, it turns out that if a function is fresshe differentiable, it's also gateaux differentiable, and a gateaux derivative is very easy to compute. It's just like the usual variation of the energy with respect to some parameter. So the usual way to verify fresshe differentiability is to first compute the gateaux derivative, verify that it's a linear functional, and bounded or continuous with respect to the chosen norm. If these two criteria are satisfied, linear and bounded, then the gateaux derivative is also the fresshe derivative. Okay? In general, a gateaux derivative by itself will not verify these criteria, and so will not in general be a fresshe derivative. We need also to show that if you replace the fresshe derivative in the fresshe expansion, if you replace it by the computed gateaux derivative, the remainder is small o norm x. So that we verify then that the computed gateaux derivative, which I say is easy to compute, is in fact a fresshe derivative. Okay? And a reference which has a nice discussion of this issue here. The gateaux derivative is just a conventional derivative. So you perturb the state, let's say 0, in some direction. You have a fixed vector v and a scalar lambda. This defines for a fixed v, this defines a function of lambda alone. Take the difference quotient and pass to the limit, and that's just a conventional derivative with respect to lambda. We call that the gateaux derivative at 0 in the direction of v. Okay? So in this case, if this limit exists for all v, then the functional is gateaux differentiable at 0. Okay. So this implies that the gateaux differential is just the conventional derivative with respect to lambda of the energy when the argument is replaced by lambda times some fixed vector v. The vanishing of this is what we call the first variation of the energy being 0, principle of virtual work. Okay? And this is a straightforward exercise to compute this. Okay? And we can do the same for the second gateaux differential. Is it just working now for the first time? Because I can hear myself now, somehow. Okay. So the second gateaux differential is just the same thing, two derivatives. We can show that if epsilon is fresshe differentiable, then it's gateaux differentiable, but not necessarily the vice versa. So if we have fresshe differentiability, we have this. Put an x equals lambda v with a fixed v. Here S is arc length in our rod. Then we have this, right? So that the difference quotient here is just this plus some remainder divided by lambda. And by the definition of gateaux derivative, the limit of this difference quotient is just the gateaux derivative, which will then be the fresshe derivative plus the limit of this. So if this limit is 0, then fresshe reduces to gateaux. Okay? So the lambda here is just this by definition. So this limit is this, but we already decided, this is a fixed vector. We already said in the definition of fresshe differentiability that this R1 is small o x. So this limit disappears. So that establishes the result that a fresshe differentiable function is gateaux differentiable. And the gateaux derivative is just the fresshe derivative in that case. The converse is not true, right, in general. However, there are instances, many times it is true. It's true if we can show that this fresshe derivative is linear. That's easy, typically. But mainly we have to show that it's bounded, like so. And that this limit is 0, so that the remainder is small o, norm v. If we can verify these conditions, then we can say that the gateaux derivative is in fact the fresshe derivative. So we need these additional conditions on the function in order for the gateaux derivative to be fresshe. And similarly for the second fresshe and gateaux derivatives. Okay? So if we can show that the second gateaux derivative, which is just two derivatives of the energy with respect to lambda at lambda equals 0, if we can show that it's quadratic and if it's bounded above, and if the remainder then in the gateaux expansion is small o norm v squared, then the second gateaux derivative is the second fresshe derivative as well. Okay. Okay, so we will need a formula called the Lagrange formula, which is simply an extension of the idea of the mean value theorem for an ordinary function defined on an interval between a and b. So the mean value theorem, which is a special case of the Taylor theorem with remainder, is simply this. F at b is f at a plus the interval size times the derivative at some interior point. The proof of this relies on the compactness of this interval on the real line. Okay? There's no analog, therefore, for the fresshe differential, the fresshe derivative of a function defined in a function space. So there's no direct analog of Taylor's theorem with remainder for the fresshe derivatives. But there is for gateaux derivatives. Because in the computation of the gateaux derivative, we have E evaluated at some lambda times a fixed vector, which defines a function of lambda. Okay? And if we pick, say, lambda between 0 and 1, then we can say f at 1 is f at 0 plus the interval size times the derivative at some interior point between 0 and 1. So this is just Taylor's theorem with remainder applied in this case. And here, of course, the derivative is defined in the usual way. And this is remembering what f is. It's this difference quotient. Alpha is fixed. Mu is the variable which approaches alpha. Approaches 0. And in the end, this gives us the definition of the gateaux differential in the direction of v, evaluated at alpha v. So this establishes the so-called Lagrange formula for a gateaux differentiable functional. The functional at any x is the functional at 0 plus the gateaux differential at some intermediate in the direction of x along a ray through the origin, right? 0 less than alpha less than 1. And you can use then, again, by using Taylor's theorem with remainder for ordinary functions. In the case of a twice differentiable function, that means we have a twice gateaux differentiable function. This is then Taylor's theorem with remainder, or in this context, the Lagrange formula for a twice gateaux differentiable function. Okay? There's some alpha between 0 and 1 such that this is true in that case, if the function has two gateaux derivatives. So a few minutes left, I think. Okay, so let's go back to our physical problem and look at motions without twist, just as a special case. So we have a forced rod clamped at one end, clamped at the other, but the motions here are unrestricted horizontally. We have a position on the rod, so this is our nonlinear problem. The initial configuration and the deformed configuration in the plane. And the displacement, which is our perturbation of this configuration, has two components, let's say, along the initial basis, which defines two components here in terms of R1 and R3. So this is the 1-3 plane, like so. And here's our potential energy. And I'll skip a few steps. In the case of plane deformation, it's just this 1/2 the flexural stiffness times the squared curvature of the deformed state. And we can compute that in terms of these displacements, 1 and 3. And we can use inextensibility, as Professor Luongo mentioned yesterday, to make, say, U1 a slave, so to say, to the master U3, which is the transverse displacement. So this says that U3 prime squared must be less than 1 from inextensibility, and also 1 plus U prime, U1 prime squared, which means U1 prime must be negative. So U1 must, as the rod vibrates transversely, it must shorten the rod, right, to maintain inextensibility. So we can solve this for U1 in terms of U3, and there are two possible routes. Let's pick the one that makes sense when there's no deformation. When U1 is 0 and U3 is 0, we need to get 1 equals 1, so we'll pick the positive root. So that in small enough motions, this positive root always applies. And this is the horizontal deflection derivative in terms of the transverse deflection. Okay? Okay, so then we can compute the energy in terms of the transverse deflection, provided U prime squared is less than 1, strictly. U prime is U3, and we have this always satisfied. We'll assume it's strict, and then this makes sense. So that's the nonlinear strain energy function in terms of the transverse displacement. A load potential like so can be written, this involves this is simply the change in horizontal position at the end of the rod. Can be written as an integral over the transverse deflection. And let's see, so the point is simply to set up the expression for our energy functional in this case. And we arrange it so that there's a constant in the choice of the potential energy. We'll choose it so that when there's no transverse deflection, there's no energy. So this is our energy functional in terms of the one unknown, which is the transverse deflection. Now what we need to do is verify all of the foregoing program. We need to verify fresshe differentiability, we need to, with respect to an energy norm that we compute, the energy norm is just based on F equals 0, evaluated when there's no deformation, essentially. So first we'll compute the gateaux differential. That's easy to do. So fix U0 and consider a variation like this, which depends on lambda, the lambda that appears in the definition of gateaux differential, with a fixed function v. And of course we must choose these to satisfy whatever kinematic boundary conditions we have. So this defines our function of lambda. Ultimately we'll choose U0 to be 0, which is the straight configuration under load. Yeah.
You are the end of choosing this.
We haven't made a norm yet. I'm going to construct the norm in a moment. We will construct the energy norm. This is the energy at any state. We'll construct the energy norm, which is based on the natural state, the undeformed state. So, but I need to first compute the gateaux derivatives and verify that they're also fresshe derivatives with respect to the appropriate norm. Okay. So here's our gateaux differential, and it's easy to compute. We just substitute this into here and take a derivative with respect to lambda, and then that involves u. I'll call it. I've dropped the subscript here. There should be a subscript. So we have something that depends on u and v. Okay, and that is easy to compute, although it's tedious. And you have this. It's a linear form in V, as you can see. So we evaluate this at the equilibrium U0. And U0 is supposed to be an equilibrium state. In our case, U0 equals 0, the undeflected rod. We want to see if that can be equilibrated. We've already seen that's equilibrated for all values of the force. Okay? And we see if we put U0 identically 0, everything disappears, and the first gateaux differential at that configuration vanishes for every choice of V. So we've computed the first gateaux differential. It vanishes at our fundamental state, which is the straight rod loaded with a force F. And we want now to show that this is also the fresshe differential. And we can also compute, while we're at it here, we can compute the second gateaux derivative easily. And we obtain this. We evaluate it at u equals 0, and we obtain this, right, for the variation v. This is quadratic by inspection, which is one of the requirements that we wanted to impose for fresshe differentiability. Now we construct the energy norm. Let's suppose that this is also the fresshe derivative. We'll verify it later. Then the energy norm would be equal to this. In the case of no load, right, the natural state is unloaded. So we obtain the energy norm squared by simply putting F equals 0, provided, as we'll verify later, that this is also the second fresshe differential at u equals 0. So this is simply our energy norm. And now we can introduce some inequalities, all coming from the Cauchy-Schwarz inequality. So for example, suppose we have two functions, f equal 1, and g is the derivative of something else. This is not the force, just a generic function. Okay? So Cauchy-Schwarz tells us this inequality, for example. And if we replace f by f prime, we have a similar inequality. And let's see, if we integrate this inequality with f at 0 equals 0, let's see, we have, and we maximize it, actually, yeah, then we have this inequality as well. So some standard inequalities we can generate, for example. And the integral we can show of f squared is bounded above by L squared, the integral of f prime squared, and so on. In fact, we can improve on this. We can say that this integral is bounded above by a constant times L squared, and then find the optimal constant. So the problem of finding the optimal constant is itself a variational problem, which is classical, discussed, for example, in this famous book on inequalities by Hardy, Littlewood, Polya, very old book. The optimal constant is actually 4 over pi squared. So we'll use this optimal bound. And so we can do the same thing for the alternative inequalities that we had a moment ago. And in particular, we'll need this bound here. We can introduce a sub-F norm constructed from the f prime, and f double prime, like so, and show that there's a constant, using these inequalities, there's a constant such that it's bounded above by our so-called energy norm, which was the integral of f double prime squared. Okay? This is all just to establish equivalence to a well-known norm. So we established that this so-called energy norm is truly a norm. What else? Okay, here's the second gateaux differential at our equilibrium state now, not at the natural state. We computed it a moment ago. Here's our energy norm. This will be bounded above. If we change the sign of here to a plus, we can bound this above by this quadratic function. So we can assert then that this is true from one of our inequalities here, which I forget which one, and combine these together to assert that the second gateaux differential at our equilibrium state, loaded equilibrium state, is bounded above by some constant, here F is a given force, times the squared energy norm. So we've established that the second gateaux differential is quadratic as required, bounded above. And so we only need to show that it's the second fresshe differential, we only need to compute the remainder in the fresshe expansion and show that it's small as required. For that purpose, let's use the Lagrange formula. Right? The first gateaux differential vanishes at our equilibrium state. So the Lagrange formula reduces to this for some alpha between 0 and 1. We can add and subtract the value at alpha equals 0. This would be the second gateaux differential we've just computed. And then we need to show that this is small o energy norm squared in V. And we can use the general form of the second gateaux differential to compute this difference. It's a bit tedious. And we need to show that this is small O norm V squared so that we can then claim that the second gateaux differential is actually the second fresshe differential. It's tedious to do that. There are some steps here to do that. The proof relies on the existence of a maximum value of this, which is bounded above by some constant times the energy norm. So this constant goes to 0 as the energy norm goes to 0. And some standard inequalities then. I won't drag you through the tedium of it, but it's there if you want to read it. We can show that this difference quotient ultimately is given by this bracket. And because m goes to 0, this constant m, as the energy norm goes to 0, that means this ratio goes to 0 as energy norm V goes to 0, which means this has to be small o, norm V squared. So we are fortunate that our second gateaux differential, in fact, is a fresshe differential at V equals 0, at the equilibrium state. Okay? So this is the second fresshe differential at the equilibrium state. And we will then have stability So we now have continuity of the energy, right? Because we have second fresshe differentiability. We want to solve this problem. We want the second variation, the second gateaux differential at equilibrium, to be bounded below, like so. This is the additional step remaining for the proof of the Lagrange-Dirichlet theorem. And why don't I stop there so that we can have a break. So remember now, this is the only remaining step. We need to show the lower bound with a strictly positive lambda on the second fresshe differential. Thank you.
So can I assume, we discussed a few seconds with them, so
Yeah.
you control the second derivative
Yeah.
in the case of the beam,
Yeah.
then you do not allow anyone to the end of the
Yeah. No, that
will be too high.
no, that will be controlled by the energy norm.
Yeah.
That's okay. You can let n go to
It
infinity.
will become infinite, that's normal. In this,
Well, so long as the energy remains bounded, I guess, you're right. In that case, the curvature locally becomes unbounded, so the energy
when n
Yeah.
tends to infinity,
Yeah.
this norm
will blow up.
tends to infinity.
Yeah. That's right. Now, what's interesting before we stop, this program of establishing the existence of the second fresshe differential can be carried out for rods here, and it can also be carried out for plates and shells. The reason is the existence in the energy functional of a second derivative. So therefore, this program, that's the reason, it turns out. This program cannot be reproduced for conventional finite elasticity, in which the energy depends only on one derivative, the deformation gradient.
Unless you introduce higher.
So Coiter, in fact, extended the theorem by saying, okay, in practice, if you have, in practice, in a normal problem, you cannot experimentally detect the strain gradient energy, the higher order gradient, in a typical problem. We can add it, therefore, without destroying the practical applicability of conventional elasticity. If we add the smallest regularizing term, with second derivatives and displacements, we can improve fresshe differentiability, carry through the whole program, and prove Lyapunov stability. There are some incorrect papers written in which it was claimed a priori that standard finite elasticity is fresshe differentiable. It's incorrect. One of Coiter's colleagues named Martini proved a function of f alone, the deformation gradient, is fresshe differentiable if and only if it's a quadratic function of f. But such cases are ruled out by objectivity.
Yeah.
So it works for structures, which is good because this is the typical application for stability theory. But it does not work for finite elasticity unless we regularize finite elasticity. I mention this because Professor Delisola here will talk to us tomorrow about a strain gradient theory. Right?
He said we have to do it.
Yeah. Okay, so we stop.